We are going to introduce now a new type of compound that you may have not seen before, and that compound is called a coordination compound. It's also called a metal complex, a metal coordination complex. It's a new kind of compound, and the way to understand what this compound has that other compounds do not have, it may be good to understand how it is formed. So a way to understand how a coordination compound is formed is by understanding it as an acid-base reaction. And let's remember that based on the definition of a Lewis acid is a species that is lacking in electrons, so it accepts electrons. And a Lewis base is a species that has an excess of electrons, so it gives electrons. So remember that, well, an hydronium and an hydroxide, they all fit into the more general definition of Lewis, of acid-base definition of Lewis. So let's try to understand how a coordination compound formation can be an acid-base Lewis formation. So you have your metal, and your metal will accept electrons, and this metal, and by the way, typically it's a D metal, meaning it's from the D block. It's transition metal, not sodium, not magnesium, not from the alkali or earth alkali columns. So it's typically a transition metal, and this metal accepts what we call a ligand, and this ligand acts like a Lewis base, giving those electrons to the Lewis acid. And this new compound is formed. The new compound is what we call a coordination compound. And this compound is a new molecule. So the bond between these two is not ionic. It is not just pure charges interacting. This is why sodium and magnesium do not form metal complexes. Even though they're metals, they would form only ionic. In this case, this new compound forms a new molecule, and if this molecule is charged, it will probably be soluble in water, and water cannot break this bond. Unlike ionic compounds can be broken, can be hydrolyzed by water, but water cannot break this bond between the metal and the ligand. So let me give you some examples so that we can see exactly what coordination compound looks like. So here you have a bunch of examples of coordination compounds or metal complexes. Typically they are between these kind of brackets to indicate that it's an entity in itself. So do not try to split between these, because it's a fairly strong kind of bond between the metal and the ligand. And typically the ligands, and that's an important distinction, the ligands will have identity by itself. So there is the chloride, there is ammonia as ligands. Okay, so it may be a good exercise to go through a true-false kind of questions to understand a little bit further what a coordination compound is. So let's go through here from A to E to see if these questions are true or false. Let's say the metal is a Lewis base and the ligands are Lewis acids. That's quite the contrary, right? So we said that the metals in here, they accept the electrons, so they act as Lewis acid. So it's actually the metal is a Lewis acid and the ligands are Lewis base, because the ligands give the electrons. Now, only complexes with coordination number 6 are found in nature. What is the coordination number? Coordination number is either the number of ligands around the metal or the points of contact that the ligands have with the metal. In general, with all these examples, each ligand has one single point of contact with the metal. So true that this coordination number for this coordination compound is 6. This one is also 6. Notice that for this one is also 6. 4 plus 2 is 6. It has 6 ligands around, but this one is 2, this one is 5, this one is 2 again, this one is 4, and this one is 6 again. So it is not true that there's only a coordination number 6 for metal complexes. Now, see, there are coordination complexes with sodium and magnesium. Well, no, that is not true. As we said, sodium, potassium, magnesium, calcium, these ions, these cations, while they're still metals, they're very happy with their noble gas configuration. This means that they pretty much act like point charges, just like point charges, and by that we mean that they just form ionic bonds with the anions. So because they do not have the complexity of the d orbitals that iron, silver, chromium, vanadium, copper, chromium, gold, cobalt, these metals do not have the complexity of electrons that the transition metals have. They do not form the coordination compounds. These do not form this new type of molecules that water cannot take apart. Any compound that these can make, water can take it apart into the anions and the cations. Now so therefore this is false. So metal complexes are always neutral. That's typically a misconception. That is not true. This one is neutral, but this one is not. Neither is this one. So this means that typically when the metal complex is non-neutral, it will come with what we call counter ions. So if this one has one positive charge, they will probably come with a negative ion. And this interaction between these will be an ionic interaction, but not within the complex. Okay, and likewise, if this one is an anion, they'll probably come with a positive counter ion. So that is not true either. Okay, so none of these are true. And now let's try to understand if these compounds are coordination compounds. Well, let's see. We said that magnesium, it does not form coordination compounds, at least the way we define them here. This is purely an ionic compound, magnesium chloride. Now let's try to understand why these are not coordination compounds. We said that ligands should have an identity by themselves. When you try to dissolve this, actually you will not be able to dissolve this other than maybe iron hydroxide. You cannot have ions oxygen-2 negative floating in water. This is not a ligand. So what you have here is in this case this is an ionic kind of interaction. In this case is a covalent type of interaction. These can form, because it's charged, and can form other ionic compounds. So because these oxygens are not ligands, and in water, so this one in water, the iron oxide does not, you will not have the oxygen-2 negative. They cannot be called a coordination compound. Okay, typically you will see a transition metal and ligands that have identity by themselves. You can see them in water, so that when they get together they form a molecule of their own. Okay, and the last one, why is aluminum chloride not a coordination compound? If you dissolve aluminum chloride, you will not have entities of aluminum chloride in water. If anything, water can split aluminum chloride into this. So if water can split it, it means that this is mostly ionic. It has a percentage of covalent bonding, but it's mostly ionic. Therefore, this is not a coordination compound. We will see more and more examples, and hopefully you get the idea, but the take-home message is that a coordination compound is a molecule that water cannot take apart. It means it's not an ionic type of interaction, and it satisfies both the metal and the ligand in this acid-base Lewis kind of definition.